Okay, so let's get started with the second lecture for the machine learning for 3D data. So last time in our introduction, we briefly discussed some of the applications of the 3D data. So we could basically classify all the applications into three or the four kind of categories, while there are also many other applications as well. So some of the applications, or basically like one thing was basically the reconstruction, which is basically replicating the real world, the objects or the scenes from some kind of the sensed data. So the sensed data can be some kind of 3D scans or some kind of the multi-view images, and making this kind of some 3D reconstructions. The other application can be some 3D generation, which is not reconstructing something from the real world information, but basically making some 3D objects or the scenes from scratch. So these are some of the examples that we are basically making some kind of the 3D models without basically having any kind of the real world information. And the application can be 3D perception, which is not about basically making the 3D as the output, but taking the 3D information as input in terms of like extracting some kind of some perceptual information, like detecting the objects and also tracking some of the objects there, and basically understanding all the things in terms of some 3D environment. And these kind of techniques can be typically useful in so many computer vision and the robotics applications. So speaking to these kind of the applications, so what we are going to discuss in this course is basically how we can make some kind of the techniques that can be basically applied for those kind of the downstream applications. And for that, we are going to discuss some kind of the ideas in terms of like how we can make some kind of the deep learning techniques, especially some kind of the neural networks. And when you see some kind of the many different types of the neural networks, those kind of the neural networks can be largely basically classified into the two types of the networks. Like one can be encoder, which is basically taking the 3D data as the input and making some kind of the different outputs. And the other might be is basically the decoder, which is now producing the 3D data as basically the output. Then for those kind of the applications for this 3D perception, reconstruction, and also the generation, what types of the networks would be needed? So, please post the answer on the Zoom chat. So when you think about some kind of the applications like generation or the perception or the reconstruction, do we need like either the decoder or the encoder? So you can answer those things for each of the application. For the reconstruction and the generation and the perception, do we need the encoding network or the decoding networks? So please send a message to me. So basically, depending on the application, we would need some kind of the different some kind of the architectures, right? For some kind of the applications like reconstruction or the generation, we definitely need some kind of the networks that can produce DVD data as the output. So those are some kind of the cases that we need some kind of the decoding network, right? But for this 3D perception task, we will need some kind of networks that can take this 3D data as the input. So those are the cases that we need some kind of encoding the networks. So the thing is that in this course we are going to discuss like some different kind of the neural networks that can either encode or decode some kind of the neural network, some 3D data. And we can also think about some kind of combination of the encoding and the decoding the architectures that will be autoencoder, and we're also going to discuss that. But those are basically some kind of the big classifications of the neural networks about this 3D data. So as I mentioned last time, so we are going to discuss some kind of the different representations, like the point clouds, like implicit representation, the multi-view, many things. And for each of the representations, we are going to see like how we can design some kind of the encoding networks or the decoding the networks. And based on those kind of the architectures, we are also going to see how we can apply those kind of the neural networks for those kind of the different applications. So that's the main thing that we are going to discuss in this class. And let's get started with some kind of discussion about the 3D representations. So the reason like why we discuss this 3D representation is that basically if we think about like making any kind of the softwares or especially some kind of the neural networks that can process some kind of the data, the thing is that we need to somehow represent the information that we have into some kind of the numbers, some numeric, some representations, right? So let's think about that, like we are making, like basically not having some kind of 3D data, but something like one-dimensional things. For example, like the, natural language. So let's think like making some kind of the LLM. Then we can basically treat some kind of the text information as kind of the one-dimensional information, right? Basically having some kind of the words. But given this kind of the text, how can you basically represent the text into the numbers? Have you learned about like some kind of the way that how we feed the text information into the neural network? Any thoughts on this? So I'm just like testing like whether you have some kind of the basic knowledge about some kind of the deep learning. If you took any kind of the deep learning course before, then you might have some kind of the idea in terms like how we typically represent the text into some numeric representations. So yeah, as you would know, I guess, the typical idea to represent the text is basically, dividing the text into some kind of the words that we also call the token. So that's the process that we call like the tokenization, right? So once we basically split the entire the text into a set of the sequence of the tokens, we also basically map each of the token into a low dimensional vector, which is through some kind of the embedding the process, right? So that's basically the way that we are basically having some kind of some numeric representations for the text in terms of like splitting the text into a sequence of the tokens and mapping each of the token into some low dimensional vectors. So all the text will be represented as kind of the set of the vectors that basically become some kind of the 2D the matrix, right? So this basically information is fed into the neural network and then doing some kind of the processing. And also for some kind of the tasks like the generation, we can consider generating this kind of sequence of the low dimensional some kind of the vectors and basically mapping these into the tokens. So that's kind of some typical representation of the text to feed this information into the neural networks. So this is the 1D case. So what also do we do for the 2D images? It's also very common to see some kind of the neural networks that process the 2D images, right? So how do we also, represent a photo into some kind of some representations with the numbers? Yeah, so I mean, 2D images are basically the same. So this is basically some kind of the 2D, some grid information. So we treat basically all the images as some kind of a kind of the set of the pixels, right? So pixel basically means the picture element, which is basically some kind of the one point in the 2D-dimensional space. And we basically see a photo as kind of the 2D grid of the pixels. And every pixel basically has the color information, which is typically represented as basically RGB three-channeled information, which means that we have the three numbers for each of the pixel. So which means that every image, it will be represented as kind of the 2D matrix, but actually it's kind of the 3D tensor in terms of that we are adding one more the dimension for the RGB, the color channel, right? So we are having the width and the height, and for each of the pixel, we also have another dimension for the RGB, the color channels, right? So all the images will be represented as some kind of 3D tensor, which will be also fed into our neural network. And these kind of some grid, the representations for the 2D images might be kind of the ideal representation to apply some kind of the existing, some kind of the, neural network layers, like some kind of convolution operation or the transformers. So given this kind of the 2D grid representation, we can easily apply some kind of the convolutions in terms of doing some kind of local operations. And also, we can also apply some kind of the ideas like the transformers. The idea of the transformer was also basically dividing the 2D grid into some of the local patches and applying some kind of the attention mechanism. It is clear? It is like too fast to answer the questions, or? So basically, yeah, this will be how we're gonna have those like kind of lectures. Um, so I'm going to ask some kind of the questions, and you will need to basically answer those questions in the Zoom chat. Clear? Yeah, so those are some kind of the basic idea in terms of basically how we handle some kind of the 1D and the two-dimensional data, some kind of the text and the images and also kind of audios and many other things can be basically processed into this way, basically having some kind of the 1D grid or the 2D grid kind of things, right? So given this kind of some the techniques to process some kind of the 1D and the two-dimensional data, what would be kind of the best way to handle some kind of the three-dimensional data? So what would be kind of the some most straightforward kind of extension from the 1D to the 3D? Obviously, it's some kind of a straightforward way to extend those kind of things into the 3D grid, 3D data. We'll be basically having some kind of a 3D grid, right? So as we have some kind of the 2D grid for the images, having the picture element, basically having the element in the matrix, we can also consider having some kind of the volume element, which means that we're having the 3D grid of the voxels. So in the cases that we are having the 3D grid, each element of the 3D tensor will be called as the voxel, the volume element, right? Then once we have this 3D grid, then we can basically apply all the information we have used for the 1D and the 2D data in terms of having some kind of the convolution operation or some kind of transform or the many other things. And this kind of the approach can be especially useful for some kind of the medical data. So actually, many kind of the medical data are also represented as some kind of 3D data. So if you take some kind of the CT scans or the MRI scans, those are basically provided as some kind of 3D, some volume information, basically giving some kind of information about some kind of human bodies, some organs, right? So for those kind of cases, since we really have some kind of the volume information, we can really consider representing all the things into the 3D grid and also applying the 3D convolution. But what are the issues, like when you basically apply this kind of like 3D convolution for the other types of the 3D data? Especially for the cases that when you scan things, when you have some kind of 3D models, what are the kind of the issues when you apply the 3D convolution? So that's the first question. Yeah, obviously the issue might be is that it's like computationally like too expensive. But also kind of the things that we are going to see is that while there are some cases that we really need to have some kind of the volume, the information, for many of the other cases, for many applications, especially like when you acquire some 3D information from some kind of 3D scans, or when you have some kind of 3D models, the issue is that mostly we are basically interested in not the kind of the volume information, but the surface information. So from the 3D scans, typical 3D scans, like what we get is basically some kind of the information about the points over the surface of the kind of objects. But we don't know about like what we have inside of the object, where we don't even care, or like what we have inside of the objects. That's also the same for the scenes as well. For the scenes, like most of the places in the 3D space will be empty. There is no information that we are encoding in this kind of the empty space. So that's kind of thing. So if we basically encode all this kind of some surface information into some kind of the volumes, the thing is that many of the kind of the voxels will be kind of the empty the voxels. So there are also kind of the bunch of the ways in terms of how we encode all this kind of 3D information into the voxels. Like one way is that we are basically encoding some kind of the occupancy information, like which voxels is basically inside, while which voxels are located in the outside, right? Well, the other way around, in terms of basically encoding the surface information, is that we're also checking what are the voxels where the surface is basically passing, right? For those cases, we can basically encode the voxels, like having the kind of surface as kind of like 1, while the voxels as kind of 0, basically encoding some kind of the empty voxels. So then in this kind of the case, like what can we see is that, if we see this kind of the figure here, especially like as we have some kind of the higher resolution, we can see that actually very few amount of the voxels are basically, the voxels where the surface is basically passing. Which means that this becomes really inefficient representation in terms of the many voxels becomes like empty. So as you can see, as we for those kind of the chair, as we increase the resolution from the 32 by 32 by 32 to the 128 cubic, we can see that the number of the voxels where the surface is passing becomes less than 3%. So here the question is that how resolution is defined for the voxels. Well, I mean, it's the same as the images. For the images, we can also have like 128 by 128 the pixels, right? So as we define the pixels, like define the resolution for the 2D images, we can also define the resolution in the 3D as like having like 128 voxels along the one dimension, and the 128 the voxels in the other dimension, and also the same for the third dimension. So that's basically the way that we are basically dividing 3D space into the smaller voxels, right? So once we basically dividing the space into the small voxels, if we see how many voxels are located on this surface, we can see that actually only like less than 3% is basically having the surface information. This is even the case that when the resolution is like 128 the cubic, which means that still this is quite low resolution, not basically capturing all the fine details of the given the shape here, right? So which means that as we increase the number of the kind of resolution, the number of the spells, the voxels located on the surface will become much more the sparse, right? The sparser the representations, which means that the whole representation becomes like very inefficient, very redundant representation in terms of that most of the voxels becomes like empty. So given this kind of the very inefficient representation, the thing is that we're gonna just like increase the amount of the memory and also the time that we are basically consuming to process this kind of data. While like this kind of voxel representation might have some really sparse voxels that really has some kind of surface information. So that's kind of the typical issue in terms like when you directly basically extend all the idea about the deep learning techniques that we apply for the 1D, 2D data into the 3D data. So Voxel may not be very kind of the efficient way to handle this kind of the 3D data, the 3D information, especially basically including only the surface information. But this was kind of the first attempt in terms of how we apply these machine learning techniques into especially the deep learning techniques into some 3D data. So the first attempt to basically to try to design some kind of neural network for the 3D data was in the 2015. It's exactly 10 years ago. And the first attempt was basically making some kind of the 3D convolutional neural network, as you can see here, with some kind of the low resolution voxels here. So that was really kind of the straightforward kind of extension from the 2D to 3D. While basically the downside was basically in the huge amount of the computation, the time and also the memory, while all these 3D volumes basically have some kind of the very sparse information. So to address this kind of the issue, there were some kind of the researches. We tried to basically address those kind of things. The first kind of the direction was having some kind of the adaptive, some kind of the representation. In terms of that, we are having some kind of the bigger the voxels in the empty space. So in the cases like for the regions that we know that there is no surface information, we are basically making some kind of the bigger the voxels. And then we are basically, increasing the resolution only in some kind of the local region where we know that the surface is basically located. And once we have this kind of some sort of the adaptive, the resolution of the 3D grid, we are also applying some kind of the 3D convolution with this kind of some adaptive resolution. So this was kind of possible the idea in terms of basically increasing some kind of efficiency in terms of making some 3D convolution neural network, while the implementation becomes like way more difficult because we need to somehow make some kind of the convolution the operation, which is basically performing with some kind of the adaptive resolution. So that becomes extremely challenging, but it's doable. So this was kind of the one idea in terms of how we can improve the efficiency and also the computation time with some kind of the adaptive resolution of this 3D grid, while this is still basically very challenging in terms of like doing some kind of implementation. And the other direction is also basically applying the convolution operation only in some kind of the active areas. So here also the kind of the engineering, the idea is that we are not performing the 3D convolution for the entire region, but we only see some kind of the regions that we know that the surface is like located. So only for some kind of the regions that we know that the surface is there, we are applying this kind of convolution the operations in terms of that we are saving our time for this some kind of convolution the operations. So this was kind of quite effective the idea in terms of that we can reduce some kind of lots of the waste of the computation time in the 3D convolution, but still like having this kind of the 3D data is really basically redundant representations, also taking lots of the memory and also the time. So that's kind of the issue with some kind of 3D the grid representation. It is clear? Any questions on this? So that was kind of the issue when people started to see like how we can make some kind of the neural networks for this 3D data about like 10 years ago. So that was like very simple the idea, like just directly extending the 2D convolution into the 3D convolution, but that was not very kind of the practical for many kind of some applications. And the other way around, like the people also started to see in the 2015 was basically treating all the 3D data into a set of the images. So that was also the attempt to basically have some kind of the multi-view image representation. So here the idea is like very simple. Like we just like using some kind of the computer graphics pipeline, we render the 3D model or some 3D data into some of the images from all different views. So this is kind of the example that we're having some 3D model here, and we are basically placing the camera around the object and render some kind of the 2D images like this. And the good thing is that we know how to handle all the 2D images using the neural network, right? So we can employ any kind of existing convolution or some kind of transformer the architecture to process those kind of 2D images. And the only thing that we need to do is that we just need to aggregate all the information coming from some kind of like different images. So that's basically involving some kind of the pooling operation. And based on the pooling, we can do all kinds of things. So we can basically do some kind of classification or the segmentation, whatever that we could see for the image cases. And this was also kind of the things that people were also trying at the same time in 2015, because this was quite straightforward idea in terms of that we don't need to make any special neural network. We can just like hire any 2D neural networks to process the 3D data. It's very easy, right? And the good thing is that actually this representation was quite effective in terms of getting some kind of good result. So compared to the Voxel, which was like using some kind of 3D convolution, actually having some kind of the multi-view images and having the 2D convolution was more effective in terms of getting some kind of the higher the performance in some kind of the many kind of the tasks. So this is like one of the very representative the task, and which is also very simple, relatively the simple the task in terms of like doing some kind of the classification that we are also going to discuss next time as well. So this was the case that we are having some kind of the bunch of the 3D objects that should be classified into the 4T classes. And then we are training the neural network in terms of classifying all the kind of input 3D models into those kind of 40 classes. And you can say that compared to the neural network, which is using the 3D convolution, the network which is using the 2D convolution from the multiple images is achieving some kind of higher the accuracy, as you can see here. So that is the kind of thing. Yeah, so it's good thing in terms of that we don't need to have any kind of some specialized the network for this 3D data. And this idea also has been extended to the segmentation as well. So in terms of the what we can do, not for the segmentation, but also for the but not for the classification, but for the segmentation is that we can also do the same thing, like rendering the 3D object into the multi-view images and doing some kind of the segmentation, and then projecting the 2D segments over the 3D the surface and aggregating all the 2D segments over in the 3D space and basically getting the final results. And if we make all this kind of the process, like aggregating the 2D segments in the 3D as kind of some differentiable operation, then we can also basically run the backpropagation from the final the 3D segmentation all the way to the 2D segmentation of the neural network. So this was kind of the extension from the multi-view based 3D classification into the multi-view based the 2D segment, the 3D segmentation. So what's the flow with the multi-view? So yeah, we are going to see. So yeah, that's actually my question. So it seems like this is kind of good in terms of the multi-view images can be really good for some kind of the encoding to process the 3D data. And also kind of the good thing of the multi-view image representation is that especially if we have not only some kind of the shape information, but also some kind of the appearance information. So if you took the compare graphics course before, for the 3D the shape, we can have not only some kind of some geometry, some shape information, but we can also assign some kind of the color information. Like for the human face, the shape, we're gonna assign some kind of black color for the hairs and some kind of the skin color for the face, for those kind of some appearance information. For those kind of cases, when we have some additional, some kind of the color information or some appearance information, then that can be also very effectively handled by rendering all these 3D things into the 2D images, right? So doesn't that mean that the voxels didn't have the color? So it depends. I mean, it depends on what sort of the 3D data we have. So typically, if we just use some kind of 3D scans, those 3D scans will only provide the color information, the geometry information, sorry. But typically, all these 3D scans come with some kind of the RGB camera, which means that there will be some kind of the accompanying some kind of color information coming with some kind of geometry information. So it really depends on the 3D data that we have. But what I'm saying here is that if we do have some kind of the additional some appearance information coming with some kind of geometry information, that can be also effectively handled with multi-view representations. So it sounds good, right? Then what would be some kind of the downside in terms of having some multi-view representations? What's the flow with the multi-view representations? So I don't know whether you have noticed from the table here, but also as some of you mentioned in the answer, one kind of thing is that to precisely represent all the information for the 3D data, actually we need lots of the images. So you can see that for actually this classification result, you can see that actually we have used the 80 images for one single 3D object. So it becomes compared to some kind of typical image classification, which is using a single image for the classification. This becomes a task that we have some kind of the 80 images for a single the object, which is also still not very efficient representation. So to get some kind of the high, good quality of the outputs, actually we need some lots of the images, which is also making the process to be very inefficient in taking lots of the memory and also the time as well. So that's kind of issue. And also, while it might be good for some kind of encoding, actually this kind of like multi-view images might miss some kind of some information of the geometry, especially like if we do not have some kind of the enough the views of the images, there might be some regions that are occluded from the most of the views. Then for those kind of the occluded regions, we are basically missing some kind of some 3D information there, right? So to not to miss any kind of the details of the given the 3D information, actually we need to have the images from the many other views. This also make that the representation to be very some kind of the inefficient, so very very the high cost in terms of like processing them. Is this clear? So that can be also kind of the downside in terms of like using some multi-view representations. Any questions on this? So that was kind of also the motivation in terms of like, what sort of the other representation we need to also explore in terms of like more the efficiency in terms of the processing and also the generation as well. So the other types of the representation also people started to look into for the deep learning kind of techniques was to basically point cloud. So what was the question? Yeah, so it's okay. So the point cloud representation, as I mentioned last time, is kind of the simplest representation in terms of like we are representing all these 3D as some kind of a set of the points. So here, basically, we don't really care about like how those points are basically connected to each other. We are just having a set of the points. So that's why we call it the point cloud. So basically, we have the collection of the X, Y, Z coordinates. And additionally, we can also have some kind of the RGB, the colors or whatever kind of things. Typically, also what we have is basically the surface, the normal information. So what the surface normal is that basically for each of the given the 3D shape, we can consider define some kind of the tangent plane, right? Locally fitting some kind of the local surface with the flat the plane, right? So given this kind of some tangent plane, then fitting the local region, we can define some kind of the outgoing direction. Make sense? So for each of the point, we can also define some kind of each position and also the outgoing direction, which is the perpendicular to the local surface of the 3D shape. So that's the surface normal information, and we're also going to discuss some more details about that later. And this normal information is quite useful for many tasks, especially the conversion to the other representations. So we are going to see. So we can consider having some kind of the X, Y, Z coordinates plus some kind of the additional information like the surface normal or some color information, but basically having some kind of the set of the points. So this is the typical some point cloud representation. And this is kind of not some kind of new, some kind of invented representation, but actually this was quite, this is the representation that has been used for the long time. The motivation was like coming from the 3D scanning the devices. So actually we started to see some kind of some more practical, some 3D scanners from like more or less like 2000. So this kind of the huge scanner for the Michelangelo, the statue was like developed in the 1999 or the 2000. And so at this time, we start to see some kind of some real, some practical, some 3D scanners. And these 3D scanners are basically giving the 3D information as the point cloud because some kind of the mechanism for those kind of the devices is to basically shooting some kind of the rays from the projector into the 3D space and checking the intersection point along the ray, right? Basically, what's the kind of the distance where the ray basically intersects with the 3D surface. And the receiver basically receives this kind of information. So which means that for all the rays, we are basically getting some information about the intersection the points. So that's why we are basically getting some kind of the point cloud as kind of the output of the 3D scanning. So after we start to see some kind of the practical, some kind of the 3D scanners, there is some kind of discussions about like how we're gonna basically directly process this kind of some point cloud the information. Point cloud only represent only the surface. Yes, typically the point cloud also represent only the surface information because like the 3D scanners typically basically shoot the ray and check the intersection point on the surface. If we basically shoot a ray that penetrate the surface and also get all the information inside the object, there's such kind of cases, basically some kind of the MRI scans or the CT scans. So those are some kind of cases. We also get some kind of the volume information. For those kind of cases, the point cloud may not be kind of the right representation. Yes. But for many of these some 3D scanning kind of cases, so we're gonna get some kind of the point cloud as the final the output. So that's kind of the case. So the discussion was basically how we can directly handle this kind of the point cloud information for many kind of the perception the tasks. So that's obviously some kind of the requirement for many kind of the robotics and the vision the applications, right? Can you also use this idea of the 1+3 with the point cloud for represent color as well? So basically, yeah, obviously for all the point cloud, we can encode not only the X, Y, Z, the coordinates, but also some additional information like the RGB colors, as I said, or also some kind of surface normal information, which is having another the X, Y, Z coordinates for the surface, the normal, the vector, the directions. So we can obviously basically add some kind of the extra information for each of the point. It is clear? And for this kind of the point cloud the representation, the application is not only some kind of some scanning kind of things, but also for many types of some physics simulations. For like simulating some like fluctuating the solids or some fluid simulation, typically this kind of the point cloud representation is used for many applications. So, and we are also going to see how we can also process this kind of the point cloud data. But the good thing of this kind of like the point cloud is that it's quite good in terms of like both processing the data and also generating the data. So next time we are going to see kind of some ideas, some architectures in terms of like how we can make some kind of neural network that can process the point cloud data. And you're gonna see that actually the implementation is quite straightforward. It's quite easy compared to making some kind of the 3D convolution for the adaptive resolution for or some kind of some sparsity kind of things. Just like having some kind of encoder for the point cloud is much more much easier in terms of the implementation. This is also quite the most popular architectures in terms, especially for some kind of encoding architectures. So we are going to see how we can basically make this kind of some encoding or decoding architectures for the point cloud. We're gonna see that this is quite convenient representation in terms of like making some neural networks for that. So it's kind of a good thing in terms of making some kind of the neural networks. But also, what would be some kind of the downside, disadvantages of like having the point cloud representation compared to the other representations? Any thoughts on this? So this is the next question. What would be kind of the downsides of the point cloud for many other the applications? Yeah, so as many of you mentioned, so obviously the kind of thing is that since we do not directly have any kind of surface information encoded on the point cloud, there can be some kind of ambiguity. For example, like when you have this kind of the point cloud, how do we know whether this kind of the points represent some kind of donut like the surface like this, or some kind of spring like this, or the shape like this? So there can be basically some ambiguity. So that's kind of the issue in terms of that we don't have any kind of the surface information. Actually, that's the reason like why we want to basically additionally encode the surface to the normal information, because the surface normal information can be useful, especially extracting some the surface information. So we are also going to discuss this kind of the conversion across some kind of representations. But basically, yeah, the downside for the point cloud is that there's no the surface information or some kind of topology information. And also the downside is that since we do not directly encode the surface information to capture all the fine details for the given this 3D shape, actually we need to have the lots of the points. So if we have some very sparse points like this, then it's really hard to basically capture all the fine details for the given the shape. So those are kind of some limitations for the point cloud. So that's why we also bring up some kind of the another representation, which is the polygonal demesh. So if you took the computer graphics course before, then you should be basically familiar with some kind of the mesh representation, which is the most popular representation to represent a 3D model in the graphics pipeline. And this is also the most compact form representing the surface, because now it's not basically having some kind of the point, but also having the edges and the faces. So you can see that basically a mesh is the kind of the graph like the structure, which is basically connecting all the dots in the 3D space, which basically means that we're having some kind of the points and the edges. So until this, like having the points and the edges is exactly the same with the graph structure, but it's actually some sort of the the graph structure in terms of that we are also defining the faces as well. So by connecting all the edges, all the vertices with the edges, now we are forming some kind of the faces that basically define some kind of the local surface in this 3D space. So the kind of the key component of the mesh is basically a set of the vertices and a set of the edges, and these are basically forming some kind of the faces in the 3D space. Especially like when you define the faces only with the triangles, those are the cases that we are having a triangle mesh. And the triangle mesh is the most popular representation for the 3D models that are typically used in the graphics pipelines. So we can see that we're having the points, lines, and the triangles that are all connected to each other, defined over the 3D space. So the good thing of the mesh representation is that there are tons of some kind of the 3D models that we can see. There are lots of the online repositories for the 3D meshes. We can download those kind of things, and we can use this information, these kind of data set for training some kind of neural networks. So it's kind of the good. So here the question is that why do we need the F here? Isn't all information encoded by the V and the E? Yeah, so given but no, what we want to see is that given this kind of the vertices and the edges, actually we want to define the faces. So that can be kind of redundant, some representations, but the key is to basically explicitly define the face information in a way that they can basically represent the local surface. So that's the key idea for the meshes. Clear? Yeah, actually, you will see that it's not that straightforward to basically infer the faces only from the vertices and the edges. That's also quite difficult problem. Yeah, so basically that's kind of the mesh representation, and you can see that actually there are quite many, especially for those like ShameNet, like the 3D warehouse, like many other things. Those are some kind of representations having the meshes as the 3D data. And this is really the most popular representation, especially for the many graphics applications. And the good thing is that this is basically the most compact representation describing the surface, right? So since we have the surface information now, what we can do is that we can render the 3D object into the 2D images and making basically the 2D images, which becomes the projection for the 3D object, right? So that's kind of the applications for the meshes. And we can also apply some kind of the appearance information as well. So since we have the surface information, we can have some kind of the mapping from the surface in the 3D space into the 2D flat plane. So which means that now we can consider making a image describing some kind of some color information and warping this and stitching this over the surface, right? So in terms of that, we can now define this kind of the appearance information. So that's basically the texture, typically used in the graphics pipelines. And we can even consider not making the texture of the colors and the texture of some kind of some geometric details. So this is the case that we are basically having some kind of the offset along the kind of the normal direction of the plane. So that is also typically called the displacement map, adding some kind of the geometry details and basically warping those kind of some images over the surface in terms of like adding some geometric details. And these all the kind of things can be done with some kind of the mesh representation. And also in terms of making doing some kind of the manipulation or some deformation. When you have some kind of the surface information, it becomes like much easier to do some kind of the manipulations. We are also going to discuss this kind of deformation, the topic. probably the last week of this course. So it's good for some kind of the manipulation, and also for many other types of some kind of the physics simulation. Obviously, having this kind of the surface information can be really good. So mesh has some kind of the lots of the advantages in terms of they can be applied to the many applications. So that's kind of the good things. But what we also kind of the disadvantages for the mesh representation. So the question is that what are the downsides for the mesh representation, especially like when you consider making some kind of the architectures, neural networks for the encoding and decoding the meshes. Yeah, so as many we also mentioned, so kind of the issue with the meshes is that while it looks good in terms of some that we are having some kind of the 2D, some graph like the structure, it's actually quite, not that trivial in terms of how we're gonna process the mesh data. So what we can think about is that, for the images, we're having the 2D grid. And for the 2D grid, we know how we can apply some kind of convolution or some other kind of transformer, many other architectures. So we can maybe think about basically applying this kind of some convolution or the transformer, those kind of things into this kind of the mesh structure, right? But the thing is that all the images have the same 2D grid structure. So basically the connectivity of all the vertices are basically exactly the same. While for the 3D shapes, for each of the mesh, each of the mesh might have some different the structure or the connectivity of all the things. So there's kind of like no simple way that we can easily define some kind of some convolution operation or some whatever kind of the neural net the architectures that can apply to the any type of the mesh structures. This is basically making some kind of the difficulties in terms of processing the mesh data. But actually, there are also some kind of the attempts in terms of like how we're gonna apply some kind of convolution or some kind of some typical the architectures of the over the meshes as well. So one simple kind of the idea is that if we think about the 2D convolution of the neural network the architectures, the typical some kind of the 2D convolution neural net is basically involving some kind of the pooling operation, right? So this is kind of example like how we can also extend some kind of some typical some 2D neural net the architectures into the 3D mesh as well. Like one specific example. And for that, if we see the pooling the operation of the 2D convolution, what we can see is that we are progressively basically reducing the resolution of the data. So doing some kind of the downsampling in terms of the merging some kind of local regions like this. Through this kind of some kind of downsampling, we are basically pulling the information, and that's the basically essentially the layer, the component in the neural network, right? So here the question is that how can you do the same thing? How can you apply the same idea for the 3D meshes as well? So which means that if you apply this kind of some pooling the operation for the 3D meshes, we also should be able to progressively reduce the resolution of the 3D meshes, right? So for the 2D grid, we know how we can basically do some kind of downsampling, how we can basically reduce the resolution. It's very simple in terms of that we can merge some kind of the local regions like this. But when you have some kind of the arbitrary mesh structure, how we can also do some kind of the progressive, the downsampling, progressively basically reducing the resolution of the meshes. So if we can do that, then we might be able to basically introduce some kind of pooling operation for the meshes as well. For this, I'm not gonna go deep into this idea. So this is just kind of like one interesting idea. But actually, there's some kind of the very old technique introduced about like almost like 30 years ago, which is basically about like the edge contraction. So here the idea is that we are not basically applying this kind of the downsampling globally over the entire the surface, but for each of the local region, we are basically reducing the number of the faces through the operation, which is called the edge contraction. So here the basic idea is that if you see this slide here, we are basically removing two faces every time by just picking the two adjacent vertices and merging them here. So if I go to the next slide here. So given this kind of two faces, how we can basically remove these two is that I'm just like merging these two vertices, this and this, left and right. And then I'm gonna also merge the two edges, like A and the B, and also C and D as well. So these are basically attached like this, stitched like this. And then we are removing these two faces and also the edge E here. So this is the operation which we call the edge contraction, like just removing the edge. And through this kind of like the edge contraction, we can progressively basically reduce the number of the faces. And we can also do some kind of the pooling for the information defined over the edges. So for the information defined over the A and the B, these two edges, and the C and D, these two edges, we can apply some kind of the pooling like this. So this is kind of like one interesting idea in terms of that how we can also apply some kind of the convolution and also the pooling as well in terms of like extending all the 2D convolution neural net architecture the ideas to handle them into the the 3D mesh data. The on-pool operation will be lossless. For the on-pooling cannot be so on-pooling is still basically spreading out the information from the low resolution to the higher resolution. So there is no concept of like losing some information. Clear? So this is kind of like one specific idea in terms of like how we can also apply some kind of the 2D convolution for these 3D meshes. So which means that it's kind of like doable in terms of like processing some 3D meshes. Actually, there are some more the ideas in terms of then how we're gonna directly process the mesh data. But the thing is that these also all require some kind of some specialized operations, which means that the implementation becomes like much more complicated. And there are also very few cases that these kind of the architectures are really working. So while there are some kind of the ideas will be to process the meshes using the neural network, those are not very commonly used. While there are some kind of cases that still people are using some kind of the mesh processing the neural networks. But these are some kind of the challenges in terms of how we're gonna make some kind of neural network that can directly process the mesh data. So that's kind of the one thing. And also this is the aspect in terms of the encoding. But if we also think about the aspect of the decoding for the generation as well, like generating some deep meshes is also very challenging task. Because like the thing is that like if we make some random set of the vertices and the edges and the faces, the output, the mesh will not really represent some some desired some kind of a 2D surface. I mean the surface in the 3D space as we want to see. So there are lots of the cases the mesh may not represent a surface in 3D space. So if we see some kind of examples for that, some kind of this simple example might be is that given any kind of the edge, if we have like more than two like some connected the adjacent the faces like this. So this is kind of example that we are having the, like one edge here, and maybe having some kind of the adjacent the three faces like this. Then this means that locally this region cannot represent some kind of the two-dimensional surface in the 3D space, right? So this is the case that we are making not valid the mesh, which is not really representing a kind of surface, right? So this is also another case that we are basically having like joining these 3D faces at the vertex here while not stitching really the edges here, so which is basically making the gap here. So that means that we are just having some kind of point in this local region. So those are some kind of the failure cases in terms of that we are not really precisely representing some kind of the surfaces. So we typically call those kind of the cases in terms of that we are having some kind of the non-manifold the surface. So basically when you talk about the manifoldness, especially like two manifoldness in this case, which means that all roughly speaking, all the local regions can be mapped into some kind of 2D plane, which means that all the local region is some kind of representing some kind of 2D surface. So if we make some kind of any arbitrary meshes, there can be the cases that we are breaking this kind of the manifoldness, which means that we are not really having the 2D surface in some kind of local regions. Then the output may not be some kind of the desired shape that we want to see, properly describing some kind of surface. Right? And making some kind of the valid mesh using the neural network is extremely challenging problem that we are going to see. And if we also see some kind of the constraints, we might also want to basically make a kind of the mesh, which surface is basically enclosing a volume. So we basically typically might also want to see that the surface that we are making might be really representing a volume in the 3D space in terms of we can see which point is inside and which point is outside, right? So to make this kind of define the volume, we also want to make some kind of the watertight the surface in terms of that we can really split this space into the inside and the outside. So making this kind of the mesh might be also very challenging problem. And even we might also have some kind of the constraints in terms of the topology. So we may want to basically make some kind of this pure topology shape like this, or some kind of do not like the topology of the shapes. So these two are basically very different the types of the shapes in terms of the topology. And if we also start to consider this kind of some topological constraints, this becomes like making the problem even more difficult in terms of like adding this kind of constraint in the generation process. So speaking to that, I mean, so making basically some valid meshes using some kind of deep learning techniques is very challenging problem. Actually, there are some kind of there have been some kind of attempts to make some kind of neural network for that, like some kind of LLM kind of things. We can consider making a kind of auto-regressive model in terms of making all these the vertices in the faces in a kind of sequential manner. And recently, this kind of architecture also has been basically improved a lot in terms of making this kind of very fine meshes. So while this is really the challenging problem, these days we are also seeing some kind of advances as well, like this. So you can see that this is like basically, given the point cloud, the neural network is making the meshes like this. So the output looks really good, right? But still, it's very hard to basically guarantee to make some kind of the valid mesh as the final output. So that's kind of the challenges there. So those are some kind of the downside when you consider having the mesh representation, especially to design some kind of the deep learning networks that can process and generate this 3D data. Any questions on this? So if we go one step further, that we are not going to discuss any details, but we can also consider having some CAD representation. So CAD representation is more like complex representation, not just basically representing all the surface as some kind of simple plane, but here now we can define some kind of have some more primitives like sphere or cylinder and many other things, and all the surface is basically represented as some kind of some composition of this kind of higher level, some kind of the primitives. And this kind of CAD representation can be really good for many applications, especially for the manufacturing or some kind of manipulation or many kind of things. And there are also some attempts to make some kind of neural network that can process and generate those kind of CAD representation. While these are not the kind of the common ways to treat all process some typical 3D data. And there are also some kind of the advances in terms of making some, for example, like some CAD generation neural networks. So this is like one good example in terms of making some this kind of CAD representations as the output of the 3D generation, while the architecture is really complex. So you can also check that out, those kind of work in terms of see how we can also do some kind of the generation for those kind of things. So we may not have enough time to discuss all the CAD representations. So if we focus on the previously four representations, we can summarize the pros and the cons of those the representation into these ways. For the voxels and the multi-beam images and the point cloud and the mesh, if we see some kind of the pros and cons for each of the cases, the kind of good thing for the voxel representation is that, well, it's basically very straightforward representation. And we can also consider making some kind of some encoder of the voxels using some kind of sparse convolution. So actually it can be good for many applications. The thing is that obviously like making some good, efficient the system for some kind of the processing the 3D, the volume information might be really hard because we need to have some kind of specialized, some kind of operations for that. And also the representation itself is really inefficient in terms of that there might be many kind of the waste of the information in terms of that like many boxes might be just like empty. So that's not good. So instead of that, we can consider using some kind of the multi-view representation. So it's basically good in terms of that we can just very easily process them using some typical the 2D neural networks. And also the implementation-wise, that would be really easy to implement, right? We can just hire any 2D neural networks, right? It's really good. The thing is that also it's not that efficient representation in terms of that we might need some kind of the many images to capture all the details. And compared to that, actually, the point cloud can be really good representation in terms of that we can easily make some kind of neural network both for the processing and the generation. And the representation itself is quite efficient, especially compared to the voxels and the multi-views. If you're gonna work on the assignments, and if you start to do some hands-on work with the point clouds and the multi-view and many other things, you're gonna see that actually the point cloud is really compact representation. And even with some kind of the much smaller the amount of the information with the points, we can basically make some kind of quite effective some encoding the architectures that can do all the classification, segmentation, many things. And also the implementation-wise, the architectures for the point cloud are much easier to implement. But obviously the downside is that it also requires lots of the points to capture all the details. So typically the point cloud is not used when you need to basically encode like have some kind of the very fine detailed information for the geometry. So that can be also the downside. And also the mesh is actually really good representation for the many applications. So if we consider like using this kind of 3D data for the downstream the applications, the mesh will be the best representation, especially for many graphics, some applications. And this is the most compact representation, especially to encode the surface information. But the thing is that it's extremely hard to basically make some kind of the neural networks that can either process or generate the meshes. So that's kind of the pros and the cons for each the representation. Here the question is that while voxels and point cloud mesh are the output, isn't the multi-view a input? Yeah, so multi-view, we can also think about like making the multi-view as the outputs. So there are really some kind of the some pipelines of frameworks that basically produce 3D as the multi-view images, while the multi-view images will need to be converted into the other representation to be used for so many applications. So there are still some cases that we are making the multi-view as the outputs, but we might need some kind of conversion to be used for the many applications. So we're gonna get to that point for the conversion. Any other big questions? Actually, one more representation that we didn't discuss yet is the implicit representation. This is something that might be kind of like not that familiar for some of the people here. And we're going to also discuss more details about basically the implicit representations later. But basically the implicit representation is representing the 3D shape as kind of the function. And we're going to actually say that we are actually making a neural network that becomes that function. So instead of like explicitly have any 3D information, what we can do with the function is that we just basically encode all the, for example, like the inside and the outside information as the function. So what we can do is that we query a point in the 3D space and feeding this kind of the query point information the neural network. And the neural network basically says whether the point is inside or the outside. So that's basically a very indirect way to encode all some kind of the occupancy information into the function. And we're gonna get into some more details about this. But actually, this representation quite good for the generation. We're gonna also see like why it is good. So which means that for many kind of some generation the process, for some decoding process, actually we can consider making some kind of the implicit representation. But obviously there is no way that we can take the implicit representation as the input to the neural network, right? So this is more about basically the generation the process. And since also it's quite indirect way to represent some kind of some 3D the shape information, if we want to utilize the implicitly like represented 3D data into some many applications, we need to do some kind of the conversion we need to convert the implicit representation into the many other representations. So as you can see, there are some kind of the pros and the cons for each of the representations. So depending on like what we want to do and also what type of the data that we have, we might need to basically do some kind of conversion from the one to the other. So as we also, as I mentioned, if we basically have some kind of the multi-view images, that can be good for the processing. But if we do some kind of some manipulation or some many kind of the applications, applying to those kind of things, then we might need to convert the multi-view into some kind of the explicit, some geometry information, right? And having the meshes can be good, but if we want to basically process or do something with some kind of deep learning things with the meshes, well, we might also need to convert the meshes into the other representations. So basically, the conversion is really important as we're gonna basically handle very different types of the representations for the 3D. So that's kind of some very interesting, some characteristics about some machine learning techniques for the 3D. So we are not basically using any single the type of the representation, single representation, depending on like what we have, what types of data that we have, and what we want to do. We need to basically do some kind of conversion from the one to the other. So that's basically what we are going to do over throughout the entire semester. So the conversion is really kind of the important part here. And here the question is that what's the difference between a point cloud and implicit representation? Is the difference that they contain abstract data and volume and density? Well, I mean, point cloud is really having some explicit representation in terms of we really have the points over the surface. So at least like we know like what's the point over the surface, right? For the implicit representation, it's just like having the function. You can think like it's kind of sort of the black box function. So if we want to say whether the point is like inside or the outside, you need to basically feed this point information into the function. And the function will give us some kind of answer like this point is like inside or the outside. So the point cloud is like more explicit information in terms of like really having a set of the points over the surface. And the implicit representation is just like having some function, which is typically a neural network in the context of the 3D machine learning techniques. Yeah. So the implicit representation is typically used for the generation, not for the processing. So that's also kind of thing. So in terms of the conversion, basically what we are going to see is that, so let's see, we can have different all the types of the representations. And depending on like how we acquire some 3D information, we can acquire this 3D information as the point cloud if we 3D scan the objects, where we can basically have the 3D, the models that we download from the internet. Then there might be some CAD representation or the mesh representation. And we can basically just like capture some of the 3D information of the objects by just taking the photos from the multiple views, right? So that's another way that we are basically sensing some real world information into the multi-view images, right? And we can also generate the outputs as some kind of the implicit representations as well. So given these kind of like all different types of the representations, how we can do some kind of some conversion. So how we can convert from the implicit functions into the voxels. Do you see the idea for this? Actually, it's quite straightforward to convert implicit representation into the voxels. Next question, how we can do the conversion. Yeah, this is like evaluation. I mean, it's very simple. There's nothing complicated here. I mean, so for every center point of the voxel, we just like feed this as kind of input to the implicit function and see whether the point is like inside or the outside, right? So it's very simple. I mean, we just need to evaluate the functions for all the center point of the voxels. Very simple kind of conversion. Like, there's nothing to do, right? So converting implicit into the voxels is really simple task. How about the conversion from the mesh to the point cloud? It's also very simple, right? We just need to sample points over the surface since we already have the surface information. So this point cloud, mesh to point cloud is really also like straightforward the conversion that we just need to sample the point over the surface. Also, the conversion from the mesh to the multi-view is very simple. It's just a matter of like we just like render the images from all the different kind of the views, right? So these are like very simple and straightforward conversion. The slightly more the complex kind of the conversion might be is that like given the voxels, how we can convert this into the meshes, right? So this is like not very discrete kind of forward way that we are doing some kind of conversion. And if we only have this kind of the way for the conversion, then there's kind of some direction from the implicit to the point cloud. So along this direction, we can do all the conversions. But what if we want to do the other way around, from the point cloud to the implicit functions? So this is kind of the other way around of the conversion, right? So for that, we might need to this way of the conversion from the point cloud into the implicit function, which is also the challenging kind of task. So, but if we basically know how we can do like conversion from the voxels into the mesh and also the point cloud into the implicit function, then we can see that we can basically make the loop for all the cases here. Here also, like one thing basically missing is that from the multi-view, how we can do all the conversion to the other representations. We're gonna also see the examples for this in terms of like converting the multi-view into the implicit function as well. So if we also make the kind of loop from multi-view to the implicit function, which means that we can do all the way of the kind of converter from the one to the other, right? Are there a way to incorporate the color information to mesh? It seems the non-trivial to store the color information mesh unlike the point cloud. Yeah, that's a good question. But if you took the computer graphics course, I mean, either we can basically encode the color information for each of the vertices or the faces, but the better way is to, as I said, like we are defining some kind of the texture information, which is basically define some mapping from the 2D, the surface of the 3D mesh into the 2D plane. And from the inverse of the mapping, we are basically warping the 2D image and stitching over the kind of surface in the 3D space in terms of adding some kind of 3D, basically the color information over the surface. So that's the process which is called the texturing. We are now going to get into some more details for that. If you are more interested in the texturing, you can consider taking some graphics course. So yeah. Actually, I'm also teaching the computer graphics course in the other semesters, and you can also check out some materials from the graphics courses as well. So this is some kind of some brief introduction about like what sort of the representation that we're gonna consider and what's the pros and the cons of each of the representations, like why we need to consider all different types of the representations and how we're gonna do this kind of like the conversion from what we want to the other. So we didn't discuss any details about the conversion from the voxels to the meshes and the point cloud to implicit function. These are quite, slightly more like the complex kind of things. So we're gonna get into this kind of conversion later, maybe after the midterm. But given this kind of the set of the representations, now what we are going to do is that for each of the representation, we are going to see how we can basically process or generate those kind of the types of the data. So next time, we are going to start with the discussion about the point clouds and how we can make some kind of the encoding the architectures. Basically, they can process the 3D data, and they can be also used for some kind of 3D perception tasks, and also how we can make some kind of the simplest the decoding architectures that can also produce the point clouds as the output. So once we basically discuss the point cloud, we're gonna move on to the implicit representation and also the multi-view to 3D reconstruction and some kind of the hybrid representations and the meshes and also some kind of convergence across them. So this is kind of the plans for this course. Any questions on this? So as I said, like we are not going to have the lecture next Monday because it's the holiday, and we're going to continue the discussion on the point clouds next Wednesday. So I will see you next Wednesday. And if you have any questions on this lecture, please post the questions on this Slack. So we can also follow up the questions in this Slack. Okay. And I will see you next Wednesday. Thank you.